And at last, we are going to talk about the derivative as a function. And this is generally when you hear the idea of a derivative, this is generally what you hear about or what is referred to. So remember, this looks very similar to our definition of a derivative that we talked about at a point. And so now we're just going to say we can actually determine a derivative for all domain values. So we don't necessarily have to talk about a derivative at a point. So if we generalize our definition and we just find the derivative of a function f with respect to x, meaning we hold everything but x constant, and then we differentiate x. All this is the limit, by the definition, limit as h goes to 0 of the difference quotient. And you'll notice that in our difference quotient now, instead of a, we have x, and x is just, again, any domain value. So here, if we want to do this longhand, and you'll see in a little bit that we actually have, I don't want to say shortcuts, but shorter ways to do these problems. But right now we'll do this by using the definition of a derivative. So f of x is x cubed, and we want to find the derivative of f with respect to x for all domain values. So we'll just proceed by doing the definition of a derivative here. So f prime of x is going to equal the limit as h goes to 0. And now instead of x, this says substitute x plus h in for x. So I'm going to have in the numerator x plus h cubed minus, and then just f of x, which is just x cubed, all over h. Okay, so now I have to do algebra and expand this. So let's see, I'll just recopy this for a minute here. And now expanding this, you're welcome to FOIL it out. Otherwise, if you know other shortcuts, such as using Pascal's triangle to do this expansion, or the binomial formula, you're welcome to do that. But this ends up being x cubed plus 3x squared h plus 3x h squared, and then plus h cubed. And then you subtract the x cubed at the very end, and now this is all divided by h. So now continuing the algebra, x cubes cancel. Okay, so this is now equal to the limit as h goes to 0. This is h, not n. H goes to 0 of 3x squared h plus 3x h squared plus h cubed all over h, and everything contains an h, so I can divide each thing by h, get rid of that, and that becomes a squared. So this is the same as the limit as h goes to 0 of 3, and I'll put this in parentheses, 3x squared plus 3xh plus h squared. Okay, and now remember, if I have a limit where it is continuous, I can use the direct substitution property. So this is continuous everywhere because it's just a polynomial in more than one variable, but it's still a polynomial. So this is just going to equal to, okay, well, 3x squared. That doesn't change when I substitute in 0. And this term, well, that contains an h, so that is actually going to go to 0, and that's going to go to 0. So in the end, I have f prime of x equaling 3x squared. And so that is the derivative of x cubed, which is the same as f. Alright? So, quick demonstration on how to use the definition of the derivative. Now, like I was mentioning before, we have shortcuts. So these are right out of the notes for this module, and so if f of x has this form, then over here is the corresponding derivative. So you can see in the example that we did, we had x cubed, so p was 3. Our answer was 3x squared. Okay, and so this is also saying that, for example, cosine x, the derivative of cosine is minus sine x. And then similarly, the only one that's a little deceiving is this exponential one. And this is due to the chain rule, which we'll talk about in section or in module 3C. Okay, so know that that's coming, but that is the general form of the derivative. Okay, with this, we can talk about a couple quick rules. There's the constant multiple rule, where if we have a constant times a function, then and we take the derivative of that, it's just the constant stays the same, and then we just take the derivative of the function. Sum and difference, kind of like limits. If we, for example, if we had the limit of a sum or difference, it was the limit of the individual pieces. Same thing here. So if we have a sum or if we want the derivative of a sum or difference, it's the derivative of each of the components. Okay, and then there is a handout posted on ICL called Derivative Formulas, which has pretty much all the derivatives you'll need to know for the course. So please reference that, and I would recommend actually printing that out as a kind of a reference page. Okay, and so we end this module with an example. So suppose the position of ball in feet at time t seconds is given by this equation here. We want to determine the velocity of the ball at 4 seconds. So from physics, this is another note. Velocity is the rate of change in position. So in other words, we're saying that, let's see, I'll do it in green here. I'll do it in red to keep the colors the same. So this is saying that velocity, I'll redo that. That velocity at time t, this is, well, the rate of change in position is, this is position, s of t, but rate of change, derivative. Okay, so if I can find the derivative of s of t, of s of t, that will be the velocity. And then we're being asked to determine the velocity at 4 seconds. Alright, so let's go ahead and differentiate this. S prime is going to just equal, well, we have to take 64t minus 16t squared and take the derivative of that. Okay, so we're going to use the constant multiple rule first, and well, we're going to use the constant multiple rule and the the difference rule at the same time. So this is equal to 64, and then I'm going to take the derivative of just t minus 16 and then t squared and take the derivative of that. Okay, and using the kind of the table back here, we see that, okay, well, it's a power function, so the derivative is just going to be equal to, well, this has an exponent of 1. I bring that exponent down in front, so it would be 64 times 1, and then times t to the 1 minus 1, okay, which is 0, okay, but just we're going to make sure that this is described in detail this first time. So 16, and then same thing here, bring the t down, or bring the 2 down, 2 times t to the 2 minus 1. Alright, and so this ends up being 64 times 1 is just 64. This t disappears because it's t to the 0, so this is 64, and then minus 32, and t to the 2 minus 1, that is just going to be 1, so it's minus 32t. Alright, so this is the general equation for s prime of t. So this is, again, the velocity at time t, and if I want to know at 4 seconds, well, I can just compute s prime of 4, and this is going to be 64 minus 32 times 4, and I believe, after you do computation, that it is minus 64. So this just means that the velocity is decreasing at 64 feet per second. Okay, so it's slowing down in essence at 4 seconds. Alright, so a written or a description here should be provided. Again, I'm not going to write it out here, but it would be that the velocity at 4 seconds is minus 64 feet per second, meaning that the ball is slowing down at a rate of 64 feet per second at 4 seconds. All right, so that concludes the section on derivatives. We'll slowly have more tools given to us that we will use to determine derivatives of more complex functions. So that will be coming in modules 3B and 3C. All right, so that's a little brief introduction to derivatives.